Welcome. Today we are going to start our fifth chapter, multiple integrals. In this chapter we shall study first double integrals, then Green's theorem and its consequences, and finally we shall study multiple integrals. We start our first module, double integrals 1. At this time, all of us are familiar with the concepts of Riemann integrals and line integrals. While studying Riemann integral, we considered a bounded function f from a bounded closed interval ab and real valued. Here the function f is called the integrand and the bounded closed interval ab is called the domain of integration. In case of line integral, we considered an open set in Rn containing the trace of a curve gamma. And here a real valued function f was replaced by a map f whose codomain was a subset in Rn. In case of double integral, the domain of integration is a compact and connected set A in R2 and f is a map from A to R. This will be clear from the following discussion, but let us start with some prerequisites. Domain and region in Rn. By a domain in Rn, we mean an open connected set in Rn. By a region in Rn, we mean a domain along with none or some or all of its limit points. Next, we study n rectangle in Rn. Let I suffix I equal to the bounded closed interval ai bi, where I runs from 1 up to n along naturals. Let these be n many bounded closed intervals where for each I, ai less or equal to bi. Now we consider their Cartesian product. Let I be the Cartesian product of I1, I2 up to In in the natural order. That means we consider the collection of all n tuples x1, x2 up to xn, where xi comes from the ith interval and I is from 1 to n. Clearly this is a subset of Rn. Such a set I is called an n-dimensional rectangle in In, or sometimes we call it an n rectangle in Rn. We know the bounded closed interval with both the endpoints A is nothing but the Singleton set A. So it may so happen one or more intervals in the above discussion is a Singleton set. Next, the above definition can be extended using any kind of intervals, open, closed or semi-open and even bounded or unbounded. In some books, we can find n rectangle is called an n interval. Now we discuss the measure of a bounded n rectangle in Rn. Let A less than B. Then the length of the bounded intervals AB open in both sides, open A closed B, closed A open B and closed A closed B is B minus A. Since closed interval with both endpoints A is nothing but the Singleton set A, the length of a Singleton set is considered to be 0. Let I1, I2 up to In be n many bounded intervals and for all I from 1 to n, I let this be ai bi closed interval. Let mu I denote the length or measure of I. If I is the Cartesian product of I1, I2 up to In in the natural order, then the measure of I is denoted by mu y. Some books denote this by mi and it is usually defined by mu y equal to product of mu i's, that is b1 minus a1 multiplied by b2 minus a2 multiplication continued up to nth term, that is bn minus an. Whenever n is 1, we call this measure length. For n equal to 2, we call it area and for n equal to 3, we call it volume. It is obvious that mu y is 0 if and only if for at least one I, mu I must be 0. A necessary and sufficient condition for this is that for at least one I is a Singleton set. Now we are going to introduce an important concept, set of measure 0. A non-empty set, a subset of Rn, is said to be a set of measure 0 or a set of content 0 if and only if the set A can be covered by a countable collection of n rectangles, the sum of whose n measure is 0. That is, for any epsilon greater than 0 arbitrary, the set A can be covered by a countable collection of n rectangles, the sum of whose n measure is 0. That means we can make the n measure as small as we please. It is trivial to verify that a subset of a set of content 0 is also a set of content 0. Now we discuss a result. A countable set in R has content 0. We prove it. Let A be a countable set in R. First we assume that A is denumerable. So we can write the set A as a sequence. Let these be the elements A1, A2 up to An and continuing. We choose epsilon positive arbitrarily. Now we consider a denumerable collection of open intervals with left end point An minus epsilon by 2 to the power n plus 1 and right end point An plus epsilon by 2 to the power n plus 1. Here n is any natural. Now one can check that the length of the nth interval is epsilon by 2 to the power n. The sum of the lengths of these intervals can be expressed as a series epsilon by 2 plus epsilon by 2 square and so on, and whose sum is convergent and is epsilon. This shows that the set A can be covered by a countable collection of intervals, sum of whose lengths is less than any pre-assigned quantity, however small. Thus, A is a set of content 0. From this it is clear that the case when A is finite is trivial. Next result. Let us consider a denumerable collection of sets in Rn, each of which is of measure 0. Let them be A1, A2, An and so on. Then their union A equal to union Ai is also a set of measure 0. The proof of this result is similar to the previous one. Next result. In R2, any line segment is a set of measure 0. In a similar manner, in R3, any bounded portion of a plane is a set of measure 0. For the first one, let the length of the line segment be L. Now let epsilon be arbitrary. We consider a rectangle containing this line segment whose two sides are parallel to this line segment and breadth is epsilon by L. Then the area of this rectangle is epsilon, hence the result. For the other case, the proof is similar. Another result, if M is strictly less than N, every subset of Rm when considered as a subset of Rn has n measure 0. Now a definition. Let A be a subset of Rn. A property is said to be satisfied almost everywhere on the set A if and only if it is satisfied on the set A except for a subset of n measure 0. With this preparation, now we are going to introduce the notion of double integrals. We start with integrals on functions defined over the Cartesian product of two bounded closed intervals and then move on arbitrary bounded sets in R2. First, we discuss partition of rectangles in R2. Let AB and CD be two bounded closed intervals where A is strictly less than B, C strictly less than D. Also let Q denotes the Cartesian product AB cross CD, which is a subset of R2. Now we consider two partitions, say Px equal to A equal to x0, x1 up to xm equal to B of AB and Py which is C equal to y0, y1 up to yn which is D of CD respectively. If we consider all the horizontal and vertical line segments in Q passing through the points xi, yj, where I runs from 1 to m and j runs from 1 to n, then it divides Q into mn many subintervals given by Qij equal to Cartesian product of the subintervals xi minus 1 xi and yj minus 1 yj. This partition is referred by the symbol px times py. The following points are to be noted. Sum of the area of all these subrectangles, that is sum of area of qij, equal to area of q, that is d minus c into b minus a. The collection of all the horizontal and vertical line segments in q which induces the partition has two measures 0. Any refinement of px or py or both induces a refinement of p equal to px times py. If p dash equal to px dash times py dash, where px dash is a superset of px and py dash contains py is such a refinement, then p is a subset of p dash. We say p dash is finer than p. Norm of a partition. The norm of a partition defined as follows: if p equal to px times py in R2 is a partition, then its norm is denoted by norm p and is defined by norm p equal maximum of numerical value of the areas of the subrectangles in Q induced by px and py. Now, it is easy to verify that 0 less or equal to norm of p less than equal to norm px norm py. Thus, norm p tends to 0 if and only if either norm px or py tends to 0. Upper and lower Darboux sums. Let AB and CD be two bounded closed non-degenerate intervals and Q equal to AB cross CD. Also, let F be a function defined and bounded on the set Q. Then there exist two real numbers small m and capital M such that small m is the infimum of all values f assumes in Q and the corresponding supremum is denoted by capital M. Let us consider any two partitions Px equal to A equal to x0, x1 up to xm, which is B, and Py is C equal to y0, y1 up to yn, which is D. Then P equal to Px times Py induces a partition on Q. The corresponding subrectangles are denoted by Qij equal to xi minus 1 xi Cartesian product with yj minus 1 yj for every I from 1 to m and every j from 1 to n. Next, let for all possible ij, small mij and capital Mij denote respectively the infimum and supremum of the values of f whenever xy is in Qij. Clearly, small m less or equal to small mij less or equal to capital Mij less or equal to capital M. Let us denote delta xi equal to xi minus 1, that is the length of the ith subinterval, and similar for y. We use the notation script pq to denote the collection of all partitions over Q. We construct the following sums. First, UFP, here U stands for upper, equal to summation Mij multiplied by length of the ith subinterval along x and jth subinterval along y. So, it is summation Mij delta xi delta yj, that is summation of Mij multiplied by area of the rectangle Qij. In a similar tune, we form the lower sum LFP, which equals with Mij multiplied by area of the rectangle Qij. These two quantities are called the upper Darboux sum of f corresponding to the partition P and the lower Darboux sum of f corresponding to the partition P respectively. Now, we investigate the effect of refinement of the upper and lower Darboux sum for the function f. While studying Riemann integral, we found that if we consider a refinement of a partition, then the upper Darboux sum decreases and the lower Darboux sum increases. Let us check what happens here. To make our idea clear, we insert one point each in the partitions Px and Py of AB and CD respectively. We insert a point x bar in between xi minus 1 and xi and y bar in yj minus 1 yj. We consider the refinements where P1 is nothing but Px union Singleton set x bar and P2 is Py union Singleton set y bar of the partitions Px and Py respectively. Let P dash be P1 times P2. Then P dash contains m plus n plus 1 more points than P equal to Px times Py. We further assume that norm of P less than delta. So, we denoted this by a picture here. Now, let R1, R2, R3 and R4 denote the 4 subrectangles we found from Qij. They have diagonal points for R1, xi minus 1 yj and x bar y bar. For R2, x bar yj and xi y bar. For R3, xi minus 1 y bar and x bar yj minus 1. For R4, x bar y bar and xi yj minus 1. Now, for all k equal to 1, 2, 3, 4, let mk and capital Mk denote the infimum and supremum of the values of fxy, where xy belongs to the kth rectangle. Clearly, small m lesser equal to small mij, lesser equal to small mk, lesser equal to capital Mk, lesser equal to capital Mij, and this is lesser equal to capital M. Now, we calculate the change in the upper Darboux sum for this refinement, and we find that UFP minus UFP dash, this happens to be Mij minus M1 times area of R1 plus 3 similar terms, and which is obviously non-negative. This happens in all the quantities above are non-negative. In the above, sum of the contribution of the part Q minus Qij remains same, as there were no refinement in that part. This shows that the upper Darboux sum decreases, not necessarily strictly due to refinement. However, it remains bounded below by m times area of Q. Similarly, it can be proved that the lower Darboux sum increases, not necessarily strictly due to refinement. However, it remains bounded above by the quantity capital M times area of Q. Next, let us calculate the approximate changes in Darboux sums due to refinement. We can find UFP minus UFP dash greater or equal to capital M minus small m times area of Qij. Since f is bounded, there exists a positive k such that for xy in Q, the values of modulus of fxy is always lesser or equal to capital K. Then UFP minus UFP dash lesser equal to twice k into area of Qij, that is lesser equal to twice k delta, as norm of P lesser equal to delta. For lower sums, we can deduce similar result. Next, let P1 and P2 be any two partitions of Q. Then P bar equal to P1 union P2 gives a refinement of both P1 and P2. Using the properties already deduced, we find that LFP1 lesser equal to LFP bar lesser equal to UFP bar lesser equal to UFP2. We can find a similar result interchanging P1 and P2. Looking at this, we can find that any lower sum can never exceed an upper sum. In the above, by the symbol P1 union P2, we mean the partition of Q obtained by considering all the points of partition both in AB and CD used while P1 and P2. That is, if P1 is Px1 times Py1 and P2 is Px2 times Py2, then P is Px1 union Px2 times Py1 union Py2. Now, the collection UFP where P is any partition of Q is non-empty. As we can check, capital M times B minus A D minus C is a member of this set. Moreover, this set is bounded below by the quantity small m times B minus A D minus C. So, it admits a finite infimum. Let us denote upper integral of f by Q is infimum of UFP, where P is arbitrary partition of Q. This number is called the upper double integral of f over Q. Similarly, the collection LFP, where P is arbitrary partition of Q, is non-empty and is bounded above. So, it admits a finite supremum. Let us denote lower integral of f over Q by supremum of LFP. P stands for any partition over Q. This number is called the lower double integral of f over Q. Thus, considering any partition P of Q, we find that m into d minus c into b minus a lesser equal to LFP lesser equal to lower integral of f over Q lesser equal to upper integral of f over Q lesser equal to UFP lesser equal to capital M times d minus c into b minus a. A bounded function f from AB times CD is said to be integral over Q if and only if the lower and upper integral of f over Q are same. The common value is called the integral of f over Q and is usually denoted by the symbol double integral of f over Q. An alternative formulation for double integrals can be done using the notion of step functions defined over rectangles. We discuss similar process while recapitulating Riemann integral. Here we describe the process in short. A detailed and lucid description may be found in the book Calculus 2 by Tom M. Apostol. Let Q equal to AB cross CD. A real valued function defined over Q is said to be a step function if and only if there exists a partition P equal to Px times Py of Q such that on each of the open subrectangles of Q the restriction of f is a constant function. We assume f is a step function over Q, then we can find partition Px equal to a equal to x0 up to xm equal to b and Py equal to c equal to y0 up to yn equal to d and p equal to px times py and real Cij such that fxy equal to Cij for every xy in interior Qij, where Qij denotes xi minus 1 xi times yj minus 1 yj. In such a case, the double integral of f over Q is denoted by step double integral f and is defined by step function integral fxy dx dy over Q by summation over ij Cij xi minus 1 yj minus yj minus 1. Let f from Q to R be a bounded function. If for every pair of step functions L and U from Q to R satisfying Lxy lesser equal to fxy lesser equal to uxy for all xy in Q, there exists a unique real number capital I such that step integral of L over Q lesser equal to I lesser equal to step integral of U over Q. Then f is said to be integral over Q and the unique real number capital I is called the integral of f over Q. One can easily understand that in Darboux method, we first consider a partition of Q, then consider two step function, one of whose value is the supremum of the values of fxy in the corresponding subrectangles, for another it was the infimum. One can also verify that the lower integral of f over Q equals supremum of LFPs, which is also the supremum of step integrals of L over Q, where L is any step function defined over Q satisfying Lxy lesser equal to fxy for every xy in Q. Similarly, the upper integral of f is infimum of UFPs equal to infimum of step integrals of U over Q, where U is any step function defined over Q satisfying fxy lesser equal to uxy for every xy in Q. Hence, for arbitrary step functions L and U from Q to R satisfying Lxy lesser equal to fxy lesser or equal to uxy for every xy in Q. We observe m times area of Q lesser or equal to step integral of L over Q lesser or equal to lower integral of f over Q lesser or equal to upper integral of f over Q lesser or equal to step integral of u over Q lesser or equal to capital M times area of Q, where small m is the infimum of f over Q and capital M is the supremum of f over Q. In case the function f is integral over Q, we must have lower integral equal to upper integral. So, we introduced the concept of double integral for a scalar field defined over a rectangle. Now, we shall shift to the integrability conditions. Theorem: let Q equal to AB cross CD subset of R2 and f from Q to R be a bounded function. Then f is integrable on Q if and only if for every epsilon positive there exists a partition P of Q such that UFP minus LFP less than epsilon. We start the proof. First, we assume that f is integrable over Q. By definition, the lower and upper integral must be same. We choose arbitrary positive epsilon. Since the lower integral of f is defined by the supremum of LFPs, we can find a partition P dash of Q such that lower integral f minus epsilon less than LF P dash less or equal to lower integral of f over Q and which equals with the integral. Since upper integral of f over Q is defined by the infimum of upper Darboux sums, there exists a partition say P double dash of Q such that integral of f equals to upper integral of f less or equal to UF P double dash strictly less than upper integral of f plus epsilon. Let P dash equal to Px dash times Py dash and P double dash equal to Px double dash times Py double dash. We consider a partition P bar equal to Px times Py of Q, where Px equal to Px dash union Px double dash and Py is also defined in a similar fashion. Clearly, P bar is a refinement of both P dash and P double dash. Then we have lower integral of f over Q minus epsilon less than LF P dash less or equal to LF P bar less or equal to UF P bar less or equal to UF P double dash less or equal to upper integral of f plus epsilon. This implies 0 less or equal to UF P bar minus LF P bar less than upper integral of f plus epsilon minus lower integral of f minus epsilon, which is 2 epsilon. Hence the result. Now, the other part. We assume that corresponding to arbitrary positive epsilon, there exists a partition P epsilon of Q such that the difference between the two Darboux sums is less than epsilon. Now, for any partition P epsilon of Q, upper integral of f over Q less or equal to UF P epsilon and LF P epsilon less or equal to lower integral of f. Then, the difference between the upper and lower integrals of f over Q less or equal to UF P epsilon minus LF P epsilon, which is less than epsilon. Moreover, lower integral less or equal to upper integral. So, upper integral minus lower integral is non-negative. Combining these two inequalities, we find that 0 less or equal to lower integral minus upper integral of f over Q, which is less than epsilon. Now, as epsilon is arbitrary, it follows that the lower and upper integral must be same. In other words, f is integrable. Using the estimation of change in lower Darboux sum and upper Darboux sum for refinement of a partition by inserting one access point repeatedly, the following result follows. Darboux sum. Let Q equal to AB cross CD and f from Q to R be a bounded function. Then corresponding to each epsilon positive, there exists a delta depending on epsilon and positive such that for any partition P of Q, if norm P less than delta, we have UFP less than upper integral of f plus Q and LFP less than lower integral of f minus q. From the above theorem, the following result follows. Result: let q equal to ab cross cd and f from q to r be a bounded function. Then f is integrable if and only if corresponding to each epsilon there exists a delta such that for any partition p of q, norm p less than delta implies UFP minus LFP less than epsilon. So far we discussed the integrability conditions. Now we shall study one result which will help us to evaluate double integrals. Fubini's theorem. Let q equal to AB cross CD and f from q to r be both bounded and integrable. So we start assuming the function f is integrable over q. We further assume that for all fixed x in AB, the integral c to d fxy dy, this is the Riemann integral, exists. Let us define a function g from AB to r by gx equal to integral c to d fxy dy for every x. If integral a to b gx dx exists, then integral over q f equal to integral a to b gx dx equal to integral a to b of integral c to d fxy dy dx. Proof. Let us denote I equal to integral of f over q. Let L and u from q to r be two step functions satisfying Lxy less or equal to fxy less or equal to uxy for every xy in q. One can easily understand that L stands from lower and u stands from upper. Clearly, L and u are integrable over q. Integrating Lf and u with respect to y over cd, we find integral over c to d Lxy dy less or equal to integral over c to d of f less or equal to integral over c to d of u. That is, integral over c to d Lxy dy less or equal to gx less or equal to integral c to d uxy dy. By proposition, integral a to b gx dx exists. Integrating with respect to x over ab, from the above inequality we find integral over q of L less or equal to integral a to b gx dx less or equal to integral of u over q. This shows that for every choice of step functions L and u satisfying a less or equal to f less or equal to u over q, we find integral of L over q less or equal to integral of a to b gx dx less or equal to integral of u over q. In other words, for every pair of step functions L or u approximating f from both below and above respectively, integral a to b gx dx lies between lower integral of L over q and upper integral of u over q. By proposition, f is integrable over q. So, the unique real number satisfying the above criterion must be integral of f over q. Consequently, integral of f over q equals a to b gx dx equal to integral a to b integral c to d fxy dy dx. This result has a twin result in which we change the order of integration, and that is given in the following. Let q equal to ab cross cd in R2 and f from q to r be bounded and integrable. We further assume that for all fixed y in cd, the integral a to b fxy dx exists. We define a function h from cd to r by hy equal to integral a to b fxy dx for every possible y. If integral c to d hy dy exists, then integral of f over q equal to integral of c to d hy dy equals integral c to d integral a to b fxy dx dy. With this module comes to an end. The study of double integral will be continued in the next module.